Thank you for the introduction. Hello, everyone. Thank you, organizers, for this opportunity. This is my first week-a workshop, so I'm glad to be here. So I'm Ritika Nair. I am a postdoc fellow at Oklahoma State University. I graduated in the summer of 2024 from University of Kansas. And this talk is based on a joint project with Anton Doctorman, Jay Schweg, Adam Mantuel, and Russ Woodruff. And as the title suggests, that's the crux of this paper, that we sort of give a bound for the number of facets. And if the complex has that many facets or more than that, then it will definitely be vertex decomposable. So just a quick review of the main terms we would need. So we are considering a polynomial ring or a field of characteristic 0 in n variables, and we're considering simplicial complexes on n vertices. So x1 to xn, and as we all know, we have been seeing throughout this week, we can define the Stanley-Reisner ring for such a complex by modding out by the ideal. So a quick example here. So if in our talk, whenever we talk about the simplicial complex, as we know that we write the simplicial complex as generated by the facets of the complex. So here, this particular complex, for example, it has got 4 facets, and those are 4 triangles. As you can see, it's sort of an open tetrahedron, but you're opening the flap to the other side. So there are 4 triangles here, and this is the corresponding Stanley-Reisner ring. Now, multiplicity of the simplicial complex or this ring is basically the number of facets, and we are considering pure complexes for our talk. So pure complexes meaning all facets have the same size. So the multiplicity is 4 for this particular complex, and the codimension, which is defined as n minus the dimension of the complex minus 1. Basically, what we do is we look at the size of the facet, and number of vertices minus the size of the facet is what gives us the codimension. So for this particular example, we have got 5 vertices, and the size of each facet, as we know, there are 3 vertices for each facet because it's a triangle. So the codimension is 2. Now coming to what we mean by vertex decomposability. So if we have not seen that term before, so we start off with a simplicial complex, and we need a couple of definitions for that. So first, for a vertex in the complex, let's say x1 in this example, the link of the vertex is defined as the collection of all those faces which do not contain that vertex, but if you attach that vertex, it becomes a face of the complex also. So for example, in this particular case, as we can observe, our x1 is part of this triangle x1, x2, x5. So the link is consisting of just the edge x2, x5, because to this edge, when you attach x1, it's becoming a face of the complex. Now, deletion of x1 is defined as the complex that you get when you consider all those faces that do not contain this vertex. So basically, in this example, you get rid of this extra flap standing outside, then you get the deletion. So both of these are simplicial complexes. They are subcomplexes that we get from our big parent complex that we started off with. Now, a shedding vertex. So a shedding vertex is basically a vertex that satisfies a nice exchange property. And in different books, it's defined in different ways. Like some books, it says that all facets of the deletion should be the facets of the complex 2, or otherwise facets of the link should not be facets of the deletion. There are multiple ways of defining. So to simplify and see things clearly, we are using this exchange criterion as our definition. So basically, all these are equivalent definitions. So X is said to be a shedding vertex if for any facet that contains X. So for example, the facet here that contains X1 is this triangle, X1, X2, X5. So for any facet that contains this vertex, can you sort of swap that particular vertex with someone else so that you're still going to get a face of the complex? So for example, here, if you remove x1, what you're left with is this edge x2, x5. And yes, you can attach another vertex, say x4 to it. So you're sort of exchanging x1 for someone else so that you can still get a face of the complex. Then you will say that x is a shedding vertex. So in this example, for instance, x1 happens to be a shedding vertex for the complex. So now we have the machinery to define what we mean by vertex decomposable complex. So vertex decomposability was first defined by Proven and Billera and 1980, and they defined this for pure simplicial complexes only. But later, Joyner and Wax sort of extended this definition to non-pure simplicial complexes too. So, as I said, we are sticking to pure complexes for our talk today. And it's a recursive definition. So a complex is said to be vertex decomposable if either it is a simplex. A simplex means it's just consisting of one facet. So either it's just a triangle, for instance, or an edge or something like that. So it's a simplex, or it contains a vertex x such that both the link and deletion are also vertex decomposable, and x itself is a shedding vertex. So given a complex, we want to first begin with a shedding vertex and look at its link and deletion. So link and deletion are basically going to give us subcomplexes of the main complex. So first get those subcomplexes. As you see, this is a recursive definition. So if we have not seen this definition before, we can take some time to sort of absorb it. But a nice way to sort of visualize it would be to think of it as, okay, you find a shedding vertex first, then look at these subcomplexes, which are the link and the deletion. And then we want to make sure that the link and deletion are also nice in a certain way. So you're breaking it down to smaller subcomplexes. And that recursive definition tells that you further go on finding a next shedding vertex for the deletion and the link respectively, break it down again, and ultimately we will end up getting something that is looking just like a simplex. So that's the idea here. So if this is satisfied, you would say that this is a vertex decomposable complex. Now, from algebra point of view, why do people care about vertex decomposable complexes? Because we, as we know, algebraists are fascinated by Cohen-Macaulay rings. So this is a very well-known result that if you have a pure simplicial complex which is vertex decomposable, then it is also going to be Cohen-Macaulay, which means the Stanley-Reisner ring corresponding to this complex is going to be a Cohen-Macaulay ring. Now, a property that is there between these two is shellability that I'm conveniently sort of sweeping under the rug because I'm not talking about shellability here. So, as we see, vertex decomposability is a stronger property than being Cohen-Macaulay. So, now moving forward to our main result. So, Naoki Terai and Kenichi Yoshida in 2005 gave this very nice result that if you have a Stanley-Reisner ring that has a large multiplicity, they gave this particular bound that we have over here. So, suppose you have a Stanley-Reisner ring whose dimension is greater than or equal to 2. And if we know that this complex is pure, having codimension C. So if this multiplicity of the ring is greater than or equal to this particular bound, n choose C minus 2C plus 1, then this ring is Cohen-Macaulay. That is the condition that they showed. So, multiplicity, meaning in other words, it's counting the number of facets of the complex. So if the complex has at least these many facets, then it is going to be Cohen-Macaulay. That's what they showed. And we strengthened this result by showing that this particular complex is in fact vertex decomposable. It's not just Cohen-Macaulay, but it is vertex decomposable. Now, the way they proved this in the result is by proving the Alexander dual version of this result. I will go into Alexander duality like in a couple of seconds maybe. So how they proved this is they showed that so it's known thanks to Egan Rayner that the Alexander dual of a Cohen-Macaulay complex is going to have linear resolution, Alexander dual ideal. So how they proved this result is they showed that the dual ideal has linear resolution. They used a little bit of homological algebra and machinery to do that. So the way we proved this result is it comparatively uses only combinatorial arguments by counting the number of facets using a certain inductive argument. So that way the proof is more combinatorial and little more simpler, I would say, but we get a stronger condition here. So if the complex has at least these many facets. Now, a way of looking at this particular bound, n choose c minus 2c plus 1 is the following. So if you can think of a pure complex on n vertices and having codimension c. So total number of facets possible is n choose c. So what this is saying is you start off with a full complex on n vertices, okay, whose codimension is c. Total number of possible facets is n choose c. From that, you just remove 2c minus 1. At most, you're allowed to remove 2c minus 1 from that skeleton, and then you can still land with a vertex decomposable complex. So just a small quick example. Suppose you're considering a complex on 4 vertices, and let's say we take codimension 2. So that particular number, n choose c minus 2c plus 1, will then be 3. So if you can define a complex consisting of any 3 of those facets, then it will be vertex decomposable. It doesn't matter which ones you choose. So now we try to see if this result can be strengthened to some more stronger classes, but no, apparently it's not possible, because with the same bound, we were able to get some counter examples just by considering some graphs, that we could not extend this to the class of, say, independence complexes of matroids or shifted complexes. Next question is, can you improve this bound? So no, this bound is tight. Okay, we cannot improve this bound. And we have constructed a family of examples for which it shows that this bound is tight, meaning if you start off by taking the skeleton of, you start off with n vertices and you consider the n minus c minus 1 skeleton of the complex. And instead of removing 2c minus 1 facets, what happens if you remove 2c facets? Can you still maintain vertex decomposability? That's the question. So it's not necessary that it's going to be still vertex decomposable. So we have counter examples, and the way the counter examples worked is, in simple terms, if we are going to sort of talk about it, the small example, let's consider. So suppose we are considering this complex tau on 5 vertices, okay? So we're just sort of trying to construct a counter example. So we start off with 5 vertices. Let's take codimension 2, meaning all facets are going to be triangles. So we are sort of considering the 2 skeleton of a complex on 5 vertices, okay? The facets are triangles. So as I said, our aim is to see, construct a counter example. So we are going to cleverly remove 2c facets from that to break vertex decomposability. That's our plan. Now, the way we remove is, so if we consider any vertex, for example, let's choose x1, then if you look at the link of x1, since we're considering the complete skeleton, every vertex is sort of attached to every other vertex. So if you look at the link, it's going to give us the complete graph on the remaining 4 vertices. So K4. Now, what we're going to do is we're going to use a sort of Reisner's criterion, which we know that if simplicial complex is Cohen-Macaulay, then the link of every faces are also going to be Cohen-Macaulay. So if and only if condition. So we are going to construct a complex whose link is not going to be Cohen-Macaulay, and thus break our whole condition. And an easy way from a graph point of view to make something that's not going to be Cohen-Macaulay is make it disconnected. So that's what we are going to use, because a one-dimensional complex is Cohen-Macaulay if and only if it's going to be connected. So what we did is, starting off with this 2 skeleton of the simplex on 5 vertices, we cleverly removed 4 triangles in such a way that after removing those 4 triangles, what we are left with in the new complex, if we look at the link of x1, it's just going to be this graph. Okay, it's going to be disconnected. So as mentioned there, the link is just going to be a disconnected graph. So basically, every other facet that gave connections between these, we removed those. Those are the 4 facets that we removed, so that the link of x1 is now going to be disconnected. This is not Cohen-Macaulay. Hence, this complex is not going to be vertex decomposable. So this bound cannot be improved. Now, for the rest of the talk, we are going to focus on the Alexander duality. But before going to that, I just wanted to mention one more thing. This is also a strengthening of the result in the same paper by Terai and Yoshida. So suppose we start off with the complex, which is not necessarily pure. It's on n vertices of codimension C. In that case, if your complex has at least n to C minus C facets itself, then it can be vertex decomposable. So the difference from the previous statement is that here there is no assumption that this complex is pure. All we are saying is that it has at least these many facets, then it's vertex decomposable. Well, even though the statement doesn't say it, just to give it out there, in the recipe, if you have a complex satisfying this condition, it will end up being pure. That's the reason we don't need this in the hypothesis. Okay, and once it's pure, it sort of follows as a corollary from the previous result. Okay, now going to Alexander duality. So yesterday in Maryl's talk, we briefly looked at duality for a graph. For the edge ideal, she was talking about the vertex covered. So here we are sort of going to generalize it. We are not sticking into just edge ideals. So just to review what the Alexander dual ideal is for a given complex, how we define it is we consider the complements of the facets. Okay, so we're looking at the dual ideal. So Alexander dual ideal. So for example, in this particular case, if we look at each facet, we have 4 triangles. Just take the set complement of each facet. So if we start off with, say, x1, x2, x5, the set complement is consisting of x3 and x4. So the quadric x3 and x4 will be a generator of the dual ideal. So for each facet, just take the complement set. And that's how we get the Alexander dual ideal. So from there, we can observe that whatever is your codimension of this pure complex, that's actually going to be the degree of the generators of this Alexander dual ideal to begin with. So in this particular example, as we see, we are getting an ideal which is equi-generated. They are all generated in a single degree, and it's generated in degree 2 for this example. So going to the Alexander dual version of what we saw. So as I mentioned earlier, Cohen-Macaulay rings have this nice duality that the dual ideal has got linear resolution. Similarly, there was this question, what would be the dual condition for vertex decomposability? And in 2016, Moradi and Koshahang came up with this nice characterization, which is called vertex splittability, which is the dual of vertex decomposition. So since vertex decomposition is defined in a recursive way, so is the splittability. So vertex splittability is defined as follows. So a monomial ideal is said to be vertex splittable if either it is generated just by a monomial, or if it's the whole ring, polynomial ring S, or it's just the zero ideal. Otherwise, the recursive definition is this. Instead of shedding vertex there, the term used is a splitting vertex here. Basically, both are the same. So there is some variable xi and 2 vertex splittable ideals, I1 and I2, which is contained in the smaller polynomial ring after removing xi, which satisfy this property. So if you can write I as a sum of these two. So basically look at all the generators that consider xi, that will contribute to this first component. and then everything that do not contain xi will contribute to the second component. So you can split the ideal and write it as sum of two ideals, which satisfies that the set of minimal generators of I is going to be a disjoint union of the set of minimal generators of these two, and your I2 is contained in I1. So if this condition is satisfied, we are going to say that our ideal is vertex splittable. You can split and write it in this way. Oh, okay, thank you. So I'll just wrap this up. So these are some nice observations for those who are interested further. Vertex splittability gives Betti splitting. So we can talk about Betti numbers of the ideal using the Betti numbers of those splitting ideals I1 and I2. It has linear quotients, and further, if it's equigenerated, it will have linear resolution. So from this, we can get the second corollary, thanks to Muradi and Koshahang, that the dual form of our result, which is if I is a square-free, equigenerated monomial ideal, which is generated in degree C, and if I has at least these many generators, then it will be a vertex splittable ideal. And so it will have all those properties that we just saw in the previous slide. So this is a nice corollary, and some more fun corollaries are there if you would like to look at the paper, and these are some references what I mentioned during the talk. And thank you, everyone.